All right, let's talk about something in math that pops up all over the place, and let's be honest, can look pretty weird at first. Function notation. You know, that f of x thing? If you've ever looked at that and thought, what on earth is going on here, then you are in exactly the right place. We're going to break it all down and make it super simple. So let's just get right into it. You see this? F of x. And your brain, totally reasonably, probably goes straight to, wait, is that f times x? And look, that is a super common thought. But nope, that's not what it is. It's actually more like a special kind of math code. And this is really the key to the whole thing. It's just a symbol. That's it. It's a special notation, a way of writing things. And you know what? Once you get what that symbol means, the whole mystery just, poof, it disappears. So let's crack this code together. Okay, the very first thing you need to know, the most important part, is that f of x is basically just a fancy, more useful replacement for the letter y. Seriously, that's the big secret. Think of it like an upgrade from your old phone to a new one. It does the same job, but way better. Take a look at this. On the left, the old way, y equals 3x minus 4. On the right, the new way, f of x equals 3x minus 4. These are 100% identical. They mean the exact same thing. The only, and I mean only, difference is that with f of x, we've given that rule, the 3x minus 4 part, a specific name. We've called it f. We could just as easily have another rule called g or h. It's all about keeping our equations organized, especially when we have more than one. To really get a grip on this, the best way is to imagine a function as a simple machine. It's a fantastic way to visualize what's happening. You've got an input, the machine does its thing, and then you get an output. Simple as that. So how does this machine work? It's a simple three-step process. First, the input. You take a number for x and you pop it into the machine. Step 2 is the rule. The machine takes your number and applies its specific rule to it. You know, like multiply by 3 and subtract 4. And finally, step 3 is the output. A brand new, unique number comes out the other side. That's it. Input, rule, output. Couldn't be simpler, right? Now let's talk about the official names for these things. Inputs and outputs. Your input, the x value, is called the independent variable. Why? Well, because you are independent. You get to choose whatever number you want to put in. But the output, the f of x or y value, that's called the dependent variable. And that makes perfect sense, right? Because what comes out completely depends on what number you put in. Okay, theory is great, but let's put this machine to work. Time to get our hands dirty with some actual numbers. This is where the light bulb really goes on. Okay, so let's fire up our first machine. We'll call this one machine f, and its rule is f of x equals x squared plus 9. So what's its job? Super simple. Whatever number you give it, its job is to square that number and then add 9 to the result. All right, first task. What happens when we evaluate f of 1.5? In other words, what does our f machine spit out when we feed it the number 1.5? Let's drop it in and find out. And the calculation is really straightforward. Step 1, we substitute. Everywhere we see an x in the rule, we plug in 1.5. So it becomes 1.5 squared plus 9. Easy. Step 2, we simplify. What's 1.5 squared? It's 2.25. So now we have 2.25 plus 9. And that brings us to the final step, getting the output. And there it is, 11.25. So we can say with confidence, f of 1.5 equals 11.25. Put 1.5 in, get 11.25 out. Our machine works. Perfect. Okay, you ready for another one? Let's switch things up. We're going to use a brand new machine now. This one is called g, and it's got a different rule programmed inside. G of x equals 3x minus 4. Now don't worry, the process is exactly the same. We just have a different machine doing a different job. So this time, let's see what happens when we throw a negative number at it. What's g of negative 4? What will our g machine do with an input of negative 4? Let's see. And once again, we just follow the recipe. Step 1, substitute negative 4 for x. That gives us 3 times negative 4 minus 4. Step 2, simplify. 3 times negative 4 is negative 12, so we have negative 12 minus 4, which gives us our final output, negative 16. Boom! G of negative 4 is negative 16. Okay, so now we know how this works. But the really big question is, why? Why do we even bother with this? Why not just stick with good old y? Well, it turns out this notation isn't just for show. It's a huge upgrade that gives us some serious power, especially in math and science. Let's bring this into the real world for a second. Think about a hotel. The price you pay per day often depends on how long you stay, right? The longer you stay, the cheaper the daily rate. So the length of stay in nights, that's your input. You choose that. And the daily rate in dollars, that's your output. It depends on your input. We could literally create a function for this, maybe call it rate nights, that describes this exact situation.
So what's the big takeaway here? Why is this notation so powerful? Well, a few big reasons. First, it lets us give every single rule a unique name: f of x, g of x, or even something descriptive like cost of x. It also tells you the input variable right there in the name. It's the fundamental language of graphing. But honestly, the biggest thing is how it helps us organize and solve really complex real-world problems by breaking them into smaller, named manageable chunks.
So, I want to leave you with this final thought. At the end of the day, function notation isn't really just about x's and y's on a page. It's a language for describing relationships. The relationship between how many hours you study and the score you get on a test, or the relationship between how much coffee you drink and how awake you feel. So now that you get the language, now that you can name any rule, what relationships in your world would you want to measure?